Hello, good morning, good evening, good afternoon, everybody, wherever it might be. So it is the highest time to commence this academic year, and I'm very happy to have as our first speaker MICHAŁ ZIEMBOWSKI from a neighboring Warsaw University of Technology, and he will report on his joint work with Anna Cichocka, Bio and Fun Week, and it is about going from matrices to Leavitt path algebras while building maximal commutative subalgebras. Michał, the floor is yours. Take it away.
Thank you very much for the introduction. Hello to everyone, everywhere in the world, being at my talk. Thank you to everyone who is going to listen to me about my work with Cichocka, Bio and Van Wyk, as was said. Yeah, so I want to talk about maximal commutative subalgebras of matrices and also Leavitt path algebras. So the starting point are matrices, and then we'll move to Leavitt path algebras. My background is non-commutative ring theory, so my talk is purely algebraic in nature. So I'm interested in algebraic properties of Leavitt path algebras and maximal commutative subalgebras, and looking for such subalgebras is natural algebraic, purely algebraic task. So the story starts in 1905 when Schur proved the following theorem, quite interesting, and I think that the result is very nice. For any algebraic closed field K of characteristic 0, it occurs that maximal possible dimension is smaller or equal to n squared divided by 4 flow function plus 1. And then in 1944, Jacobson extended the result of Schur for arbitrary fields K. And it is worth to mention that in 1998, Fields medalist Mirzakhani provided a consistent proof of the Schur theorem and, in fact, of Jacobson's theorem, because her proof is true and works for every field K. So in 1998, she was 21 years old, and it is one of her first papers in algebra, in mathematics, published in American Mathematical Monthly. And I want to stress that the proof is very elementary. So from time to time, I give her paper about Jacobson's theorem to my students, just to study the paper and to study the proof. And the proof is very tricky and very clever, and very nice, but elementary in nature. So I suggest, if you want to give some interesting paper to first year students, this one is very good, I think, and very nice to study. Okay, so it occurs that the upper bound n squared divided by 4 plus 1 flow function of n squared divided by 4 is sharp. So we can provide exact example of commutative subalgebra with the dimension n squared divided by 4 function plus 1 for any n. So to show you the example, we take a field K. We take n bigger or equal to 2, because for n equal to 1, of course, we have a commutative ring. Matrices 1 by 1 are commutative. So we take n bigger or equal to 1, and we take k1 and k2 non-zero positive integers such that k1 plus k2 is n. So we fix 2 positive integers. Then we consider a rectangular array, which is the set of all ij from n squared, such that a is between 1 and k1. It can be k1, and j is bigger than k1 and smaller than n. Of course, I'm aware that it would be nice. B is related to the set J, and we use B to produce the set J, which we define as all elements of n by n matrices. So we consider the set of all n by n matrices such that non-zero elements can occur only in the block, which is on the slide. So the color green, and in the white parts we have everywhere zeros. So using B, we can build the set J, as you can see. So we consider all matrices over K such that non-zero elements can be only in the gray area, and in the white area we have everywhere zeros. And so, of course, the dimension of J is what? Is K1 times K2. Yeah? Am I okay? I think so. But in a moment we will see how to use J to produce our example. Oh, sorry. Yeah. Okay. Of course, easy remark is that J to the square is 0. So if we take two elements from J and we multiply them, we get 0. So considering
yeah, it works.
It works, okay. Considering Kin, which of course In works.
Oh, now you have to talk.
Okay. It disappeared.
It's supposed to.
Okay. So if In is of course identity of the matrix algebra, we consider the center. In fact, Kin is the center of the matrix algebra. So if we take Kin plus J, so the set J, and we denote such subalgebra of M and K as A, it occurs that this is commutative subalgebra of M and K, because J square is 0 and Kin is the center of matrix algebra n by n matrices over K. And in fact, taking K1, can K2 equal n divided by 2 if n is even, or taking K1 equal n minus 1 divided by 2, and K2 equal n plus 1 divided by 2 if n is odd, we get exactly algebra A by this construction, which is of dimension n squared divided by 4 flow function plus 1. So this is what we know about maximal possible commutative, about maximal commutative subalgebras with maximal possible dimension. So this maximal possible dimension is sharp in fact. Okay. So conclusion, shows bound on the dimension of commutative subalgebra of K both universe and sharp. We can provide explicit construction of algebras which achieve the bound, and this algebra provides canonical examples of maximal commutative subalgebras. And we have key formula, which is exactly the maximal possible dimension. Interesting fact about maximal commutative subalgebras of matrices is that we don't know all of them. I mean, we don't have any classification or any construction which provides all maximal commutative subalgebras. Okay, so we know some examples, but in general we don't know. So in fact, the class I presented using the construction I showed you gives us some examples, but not all of them, because we know that there are other examples of maximal commutative subalgebras. Okay, so this is about matrices. Now I want to move to Leavitt path algebras, And I want to recall some definitions because, so it's worth it to recall some definitions, even possibly some of you are familiar with them. So we consider directed graph. E0 is a set of vertices, E1 is a set of edges, S is source function, and R is range function or range map. So of course S of E, where E is an edge from E1, is beginning point of E, and R of E is ending point of E for any E which is edge. We say that a vertex is a sink if it doesn't emit edges. So we don't have any edge going out from our vertex, and this is sink. Very important notation or very important class of graphs is row finite graphs. So row finite graphs are graphs such that only finitely many edges go out from V. So V for any V in E0. So
just let me make a brief historical comment because it kind of sounds strange. Why row? That's because first, when we were considered configure algebras, they were written in a matrix form rather than graph form. And this is like the row of a matrix which was encoding the graph. You know, okay. This is like an ancient terminology that it prevailed.
Yeah, but this is very important class of graphs. Okay, so some notations. Then, as usual, a part is a sequence of edges, E1 to En, such that ending point of Ei is beginning point of Ei plus 1 for any I from 1 to n minus 1. Beginning point of a part I is beginning point of the first edge, and ending point of pi is ending point of the last edge. So in this case, this is n. Length of pi is just n, so the number of edges appearing in pi. By pi 0, we mean all vertices appearing in pi. So this should be clear. This is just notation. And we also consider V, vertex V, as a path of length 0. So we start and stop at V. So this is 0 path with length 0. And the set of all paths is just denoted by path of V, as usually.
So you consider only finite paths?
No.
No.
No. In general, I don't. Yeah. So in this case, yeah. So I should. Yeah. So.
Well, you wrote down E1 to
Yeah. So this is you're right. Yeah.
And I mean, my question is not so completely irrelevant because if you want to have, for instance, a groupoid picture of path or graph sister algebras, you must talk about tails of infinite paths.
Yeah.
So infinite paths, but then it's getting tricky. I go infinitely to the left, infinitely to the right, and it's.
But yeah. So this not exact definition comes from the fact that for Leavitt path algebra, all elements are just related to finite paths. So this is the case, and it's reason why I hate with this definition. Okay. We say that pi is closed if beginning point of E1 is ending point of En. It's simple if this is closed, and beginning point of any Ei for I bigger or equal to 2 is not equal to beginning point of E1. And it's a cycle if it is simple and has no repeated vertices. So this is also normal definition as we know from literature and many articles. A graph is acyclic if it contains no cycles. So if we don't have cycles, then a graph is acyclic. an exit of a cycle, which is very important notation.
If you don't mind, I know it's trivial, but I cannot resist the temptation of saying this. You can easily prove that your graph is a cyclic with finitely many edges. It's a cyclic if and only if the space of all finite paths is finite.
Yeah, okay.
It's a cute little path.
Yeah, so as I said, an exit, which is very important notion because it's related, for example, to simple Leavitt path algebras. So very important notion. So exit of a cycle is just HF, such that beginning point of F is beginning point of some edge appearing in pi, but the ending point, but F is different than EI. So this is.
Wait, is it enough that it's different than EI, but can it end in a vertex which is in the loop or not?
It can, yeah.
Uh-huh.
So exit is just, we have cycle, and we have just something which is.
Okay, so imagine that I just go around in my vertex simple loop, and then I decide to double one edge. Then I consider that
it's exit.
Okay, even though it's still in the same.
Yeah.
It doesn't go to a vertex which is beyond the loop. That's irrelevant. Okay.
So, Robert. Okay. Some another part of definitions of notations. If we have two vertices, which is very important to have this notation. If we have two vertices U and V, and if we can go from U to V using some path, then we will denote it by U is bigger or equal to V. This is just kind of notation. If P and Q are subsets of V0, then if P bigger or equal to Q means that there's a vertex, there are vertices U in pi, P, and V in Q, such that we can go from U to V. It means that we can go from the set P to the set Q. In this context, for a vertex U, the notation U, from U I can go to P, and from P I can go to U should be clear. So this notation should be clear. And finally, which is also very important for us, T of P denotes the set of all vertices V, such that I can go from P to V. Okay. So sometimes in the literature, we denote this set by H of P. But yeah, in our paper we use T, and I think that the notation is so clear that we can use T. Another very important class of graphs are graphs which are downward directed. Very difficult word for me, at least for me. So we have downward directed graph if for every U and V. So I take two vertices, any two vertices, U and V. I can find W such that I can go from U to W and from V to W. Okay, so I can find two paths from U and V such that the ending point of these paths are the same. It means downward directed graph.
Michał, would you agree that this is what you mean by such a comet graph? Right?
You mean comet?
Yeah.
Yeah, exactly. Comet is, I have one cycle.
What is that period? This is strange.
So I can.
Yeah.
Which one? This one?
Yeah, exactly.
Okay.
It's good to draw a picture.
Yeah. So this is.
This is really strange because I also couldn't my screen, which is
something.
Try the blue one.
This one?
No. The one on in the panel on the left. The left.
The left. This one?
Higher?
It should be.
Right.
This one?
Yeah, I think this one might.
This is our cycle.
Yes.
And then common is just if I have another vertex which is not which doesn't appear in the cycle, then this is exactly.
You have to go into the cycle.
Yeah.
So it can come from. So it's a comet because it's like something round and with a tail.
Yeah. So I think that the word commutative is perfect.
Yeah, I love it.
I know. At one moment you can see.
And you have the non-commutative rings of Saturn.
Yeah.
Would you come back? For every vertex in E,
Yes.
so this could be this one outside the cycle.
Yes.
You have that. Oh, okay.
Because
I with this picture and this notation, I misunderstood that you have to have a direct edge to each of the
No.
vertices, but no, okay, the path exists. Okay.
So having a graph, directed graph, and having edges in E1, we defined so-called ghost edges, which we denote E star. So of course, on a picture, we can just draw. By definition, we can just draw a copy of every edge E, which has different direction. So beginning point of E star is just ending point of E, and ending point of E star is beginning point of E. So everyone, so if on the graph we have edge E, then usually okay, we have E star. Yeah. So this is also a well-known notation. And this ghost edges are fundamental definition of Leavitt path algebra, which I want to present you now. So we consider field K, graph E. The Leavitt path algebra over K is the K algebra generated. Because in algebra case, by token construction, you just take generators and give me to my hands some relations, and then I have I can construct using this procedure. I can construct algebra. So in this case, generators are all vertices and all edges E and all cross edges E star. So these are generators. And now I know I want to have relations, because at this moment, at the beginning point, using generators, I have free algebra with such generators, and now I have some relations. So the first relation is that all elements of E0, so all vertices are orthogonal. If V and W are 0, so they are orthogonal. On the other hand, every vertex is also idempotent. And so the first relation says that every vertex is idempotent, but two different vertices are always orthogonal. Now, very.
That's why the sum of vertices is idempotent again.
Yeah, this is true.
And by the way, you don't use the terminology because it's a bit of a mouthful to say non-sync, finite emitter. People usually call it regular vertex.
Okay. Yeah, but then because I defined sync, what is sync, then I use it.
No, but okay, sync of course must be defined. Infinite or finite emitter, yes, must be defined, but combination of the two, non-sync and finite emitter, is always called regular in the literature, including this Leavitt book of Gina Abrams.
So E1 and E2 relations.
By the way, your friend Zach just joined us.
Okay. Oh, yes, Zach. So E1 and E2 relations are very natural. So I mean, if we take an edge E and we multiply from the left by beginning point of E, this is just E. The same is if we multiply E by ending point of E, this is still E. Similarly for ghost edges, if we multiply, because S of E is R of E star, so if we multiply E star by ending point of E star, this is still E star. Beginning point of E star times E star is E star. Next very interesting and very interesting relation is that if we take two edges E E star and F, this is 0 if E and F are different. And this is just ending point of F if E and F are the same. So this is CK1 relation. And the last one, any vertex V which is not seen, so it admits at least one edge, but on the other hand, it admits finitely many edges. Every such V is sum of elements E times E star for all E, which are emitted by V. So this is definition of path algebra, probably well known for many people being here now. Okay, and how to work, or how to glue this story about matrix algebras and now about Leavitt path algebras. So it occurs that this connection is related to the following graph. So we can consider graph E, which is just linear path graph. I called it in this way. This graph has n vertices and n-1 edges. This is defined or presented as you can see. And this is important for us. I will explain you in a moment why. For a field K and the graph E, above, which was defined above, the Leavitt path algebra is generated by vertices V1 to Vn, edges E1 to En-1, and edges E1 star up to En-1 star. Of course, with relations as above, which are called standard Kreuzer-Krieger relations. And this is, this can be seen that this algebra encodes the linear connectivity of E. Okay. Why this is important? So important comes from the fact that for our E, our linear graph, Leavitt path algebra is isomorphic to matrix algebra over field K. So this is the very important point. And in fact, I started to be interested in Leavitt path algebra when I saw first time this isomorphism. Because since this is isomorphic, this algebras are isomorphic, so it was interesting for me to think about Leavitt path algebras in the context of matrices. This isomorphism is the following. For generators or products of generators, it sends every vertex to the matrix such that in the position II, so every vertex Vi is sent to matrix such that in position II I have 1 and 0 in any other place. So this is just matrix with 1 in position II. And any element EI times EI plus 1 up to EJ minus 1, for J bigger than I and smaller than n, smaller or equal, and such element is sent to matrix with 1 in position IJ and 0 in other places, and EJ minus 1 star times up to EI star is sent to EJI. So in position Ji, we have 1 and 0 in other places. So this isomorphism is also well known, but from my point of view, very interesting. And in the context of the Jacobson and Schur result, also very, very interesting for me, especially from the point of view of construction of maximal commutative subalgebras with maximal possible dimension I presented a few minutes ago. Okay. So some interpretation of the isomorphism. Each vertex corresponds to the diagonal matrix unit EII, each directed path, because for our E, we have only such paths. EI plus 1, EJ minus 1. So we can only go from the left to the right. And other closed edges are only of this form. And in fact, the set of all such parts and the set of all ghost parts is just the set. I think this is no, maybe So any element is the sum of monomers of this form plus some elements of the field multiplied by vertices.
Okay, let me make one more elementary comment, because I was teaching a class in Boulder about it. And there is a very important basis theorem for Leavitt path algebras. In fact, it's for cone path algebras, and in particular, it is for Leavitt path algebras. It's a special case for relative cone path algebras, and then you can have it for Leavitt path algebras as well. And this basis theorem is really quite daunting. It's very non-trivial. I proved it in my class. And this is a very beautiful and subtle theorem. And without this theorem, claiming such an isomorphism between matrices and graph histology of the Leavitt path algebras, it's finite dimension, so it's irrelevant. It's quite tricky, because once I wanted to give it as an exercise for students, prove that blah, blah, blah is a 3x3 matrix. When I tried to prove it, and I couldn't. I mean, you could prove it, but it's like reproving the basis theorem, which is tough. Okay? So I was quite surprised, because it looks like an extremely elementary example. And when you want to prove that it is indeed 3x3 matrices, you immediately bump into this issue that you need to have a basis theorem.
Yeah. Okay. Yeah. Okay, so this is just interpretation of the isomorphism. So very important point that we have isomorphism. So looking at the J I presented before, of course J is a subset of M and K. So it would be nice to see what we get in Leavitt path algebra, which is isomorphic to matrix algebra over K. What is the counterpart of J in matrix in Leavitt path algebra? Okay, so we have J in matrices, and we using the isomorphism. I recalled we want to know what is counterpart in Leavitt path algebra to J. It's not difficult. So I recall you that E is like this, so E is just a linear graph, and we want to find C, which is isomorphic image of J in Leavitt path algebra, in this Leavitt path algebra. But easy fact, quite often, and quite obvious, is that C is related to the following set of paths. So C is generated by all paths alpha with the following condition: the beginning point of alpha is one of vertices from V1 to VK1, and the ending point is one of vertices VK1 plus 1 up to Vn. So we divided the set of all vertices into subsets, such that this is partition of the E0, yeah? Because sum of these two sets is just E0, and the intersection is empty set. And C, as I said, C is graph algebraic counterpart of the block subspace J. Paths start in the first K1 vertices and terminate in the last K2 vertices. And the fact, the product of any such paths is 0. If we take alpha and alpha prime from C, the product is 0. So the same as in JK, because by isomorphism it must be the case. Okay. So this remark and this fact was the first motivation for consideration I want to present in the next part of my talk. So remember why we consider C, that this is related to J, and how it was built in Leavitt algebra isomorphic to matrix algebra over K. Okay, so we have the following definition. Let E0 and E1, so let E be a graph, and we assume that this graph has at least two vertices. I will explain you in a minute why this is important and why we assume that fact. And consider two disjoint subsets of E0, non-empty subsets, such that sum of them is E0. So that's the same situation as for isomorphic copy of matrices. Then define the subalgebra. This subalgebra is possibly without identity, but define the subalgebra of Leavitt-Path algebra as algebra generated by all monomials alpha, beta, star, such that the beginning point of alpha is in the set E0S, and ending point of B star is in E0R. Okay, so we have two disjoint sets. So this is exactly, it comes from the example. So motivated by the example, we just try to consider something like this. Of course, still, this subalgebra is subalgebra such that the square of this subalgebra is 0. So the product of two elements of this subalgebra is 0. Okay.
So why don't you just write that S of beta is in ER?
Say again.
Why don't you just write that S of beta is in ER 0?
Yeah, this is the same, but because I wanted to see that this is beginning point and this is ending point. So that,
yeah, of course.
For us, yes, yeah, this is the same as you said. I think that maybe to think about this is for me better. So cases which are related to the fact, to the situation when E0 has only one vertex. So if E0 has one vertex and E1 is empty set, then of course Leavitt-Path algebra is commutative because this is K or isomorphic. Okay. If E1 is 1, E0 is if in E0 we have one element and we have only one edge, which means that we have a loop. Then we have Leavitt-Path algebra, which is isomorphic to Laurent polynomial algebra over K. So this is commutative. And if we have E0 with only one element and we have more than one edge, then we have more than one loops. Then we know that Leavitt-Path algebra is simple, which is important for us because this simple case means that Leavitt-Path algebra is also prime. I will define what prime means in a minute. But in this case, our Leavitt-Path algebra is interesting for us, but the construction cannot be applied, because we have only one vertex. So L, K, L, I, so our Leavitt-Path algebra is uncommutative, but unfortunately we cannot use our construction.
Certainly, could you please go back to the previous slide? I'm having problems with this alpha beta star, because for alpha and beta star to be composable, then the end of alpha must be the same as the beginning of beta.
Okay, but if it's not, it's 0.
Aha, so you're happy with it. Okay,
yeah.
Okay.
Right.
All right. Okay.
We consider all such elements, but if something is non-zero, then okay.
Yeah, because typically when you study these ideals in Leavitt-Path algebras, you have them generated by projections, which is vertices, and then you look at all paths that end there, and then you star one of the paths, and you have alpha, beta, star. But this transition from alpha to beta star is at the vertex V, which generates the ideal. That's why for me it's just immediate when I see alpha, beta, star, I think, okay, the range of A and the range of beta are equal.
Yeah.
But you don't care that they just go outside and their mind multiply to 0.
Yeah.
Happy.
Okay, so I think that So this is the reason by these 3 points I presented. We assume that E0 has at least 2 elements, 2 vertices. Because in other case, we cannot. But yeah, this is the case. Okay, so basic properties. So as I said, square of our constructed algebra, subalgebra is 0. So this algebra is commutative in nature. This multiplication is just 0 multiplication. So as you can see, this subalgebra is related to our J. We considered before for matrices. And the next step is to investigate the maximality of such commutative subalgebras. So we want to use this commutative subalgebra with with products which are 0 to produce maximal commutative subalgebras of Leavitt path algebra. Of course, if we consider the center of a Leavitt path algebra, the center must be subset of any maximal commutative subalgebra. So still, we need to consider here the center of a Leavitt path algebra, but we also want to use our commutative subalgebra. We'll see what can happen. Something interesting. So I think that I had before definition of primeness. Oh, strange. Okay. So I want to recall you what prime means. Prime ring. Prime ring is the ring. Is a ring such that for any A and B which are non-zero, A times our ring times B is non-zero. So this is So for any A and or, equivalently for any one-sided ideals, for example, for left-sided ideals, I and J, if I and J are non-zero, I times J is non-zero. So there are few equivalent conditions on primeness. And this is very important class of rings.
And how does it relate to prime ideals?
So prime ideal is exactly an ideal such that R divided by the ideal is prime ring. So this is prime ring. Yeah.
Now we are talking.
So this one is this one.
Okay.
So prime ideals are just ideals such that a ring divided by this ideal is prime. And beautiful fact that Leavitt path algebra is prime if and only if A is downward direct. And my story about Leavitt path algebra when it started was the following. So because prime rings is very important class of rings, I started to think about when Leavitt path algebra is prime, and after a few days I could prove that this is exactly prime if and only if A is downward directed. So then I started to think, okay, probably someone was before me, and probably it is known. Then I found, I found paper by Abrams, Bell, and Rangaswamy about primeness. So I was a little bit disappointed, but I was also happy that because it was a very nice exercise to think about primeness and to produce to produce a proof.
By the way, you have a parenthesis missing at the end. You have a parenthesis missing after Ranga.
Here, okay. Yeah. So the center of Leavitt path algebra will be denoted as you can see. So this is just Z of LKE. And now I want to state the main theorem describing the maximal commutative subalgebra of a prime Leavitt path algebra. So the condition, so if we assume that Leavitt path algebra is prime, this is equivalent to the fact that E is downward directed. It means, as I said before, if I take 2 points, one in E0S and second in E0R, I can find path from the first one, from the second one, with the same ending point. So I can consider, for any two vertices, I can consider alpha and beta star. Okay? And I can multiply them. So for any vertices, for any pair of vertices, one from E0S and second from E0R, I have element in my algebra I constructed with the beginning point in the first vertex and ending point in second. And this is condition very, very helpful, and we use it all the time in proofs and in consideration.
And you don't care that part of your path is by ghost edges.
Say again?
And you don't care that part of your path is by ghost
Yeah,
edges.
yeah, yeah.
That's okay.
Yeah, that's okay. Yeah. So this is condition we work with, and of course proofs of all our of our main result are quite technical, and I don't want to present them, but all the time we use the downward directed assumption. So main result about prime algebras. So let E be a graph with E0 set. E0 is the set with at least two elements. K is a field, and we assume that left path algebra is prime. Take any partition of E0 such that E0S and E0R are not empty sets. Then, if E has finitely many vertices, so E is finite, E0 is finite set, and E is acyclic, so in E we don't have cycles, or E has at least two cycles, two different cycles, or E has exactly one cycle with an exit.
Sorry, let me stop you. So you can fix your graph, and by varying your field, you can change your Leavitt path algebra to be prime or not prime. Because I thought that this primeness is dictated by the downward feature, but what you write is here, let K be a field such that LKE is prime. So you are saying that you must choose a particular field to make this algebra prime, but that's what is written. Let K be a field.
So this is graphic mistake. No. This should be let K be a field and LKE is prime. Sorry, yeah.
Okay.
This should be I don't know.
That's the wrong syntax.
No. So this is good mistake.
Good, because you said that
K is arbitrary field, and
yes.
it's just I assume that Leavitt path algebra is just
so no matter how crappy your field is, if you have downward graph, LKE is prime.
Then I
Good.
So if A is a cyclic, or it has at least two cycles, or it has one cycle plus with an exit, then if I take K times 1, because in our Leavitt path algebra, if E is finite, it means E has finitely many vertices, sum of vertices identity. So K times 1 is okay. We can consider K times 1. And if we take K plus times 1 plus our subalgebra constructed, it occurs that this is maximal commutative subalgebra always, for any partition. Such that E0 and S and E0R are not empty. It means also, at the same moment, that in this case, this is the center. Because the sets are disjoint. So this is the center of our algebra. And so we have still one case when E is finitely, E has finitely many vertices, and it has only one cycle without exits. And it could occurs that if E has finitely many vertices and exactly one cycle without exits, then if we take our subalgebra constructed plus the center of this left path algebra, this is maximal commutative subalgebra. I want to say that in many cases the center is well known and well described. So in general case we take the center, but in many cases we know what it is. I will show you in a few minutes something about that. And the last situation, E has infinitely many vertices. And then, if E has infinitely many vertices, our algebra constructed by us is a maximal commutative subalgebra, which means also that the center is zero. In this case, the center is zero. So the center of prime left path algebra with four graphs with infinitely many vertices is always zero.
Why? Why?
Because center cannot be in this set, and this is disjoint. So since this is maximal commutative subalgebra, but center is always in any maximal commutative. So if center is non-zero, it's here.
Yes. And why is the contradiction?
Because here we have only paths alpha. This
Alpha,
algebra,
beta, star.
alpha beta star. This is generated by alpha beta star. So if you multiply from the right by vertex, which is ending point of beta z, on the other hand you have zero. Yeah.
Yes.
So you cannot have.
Yes. So, yeah. Okay. So things of that form cannot be in the center.
Yeah.
Okay. I've got you. Thank you. No.
I have a silly question, as silly as only a student can ask. Why do you break this theorem into these three parts instead of just writing the thesis that is common for all three, i.e. that the maximal commutative algebra is the center plus your algebra, and then moreover, if vertices are infinite, then center is zero, and if there are finitely many vertices and the negation of the point 2, then the center is just the field.
So I think that the answer is the following. For this case, three cases, we know what is the center exactly.
Yeah, but that's what I mean. You write the general that, okay, whatever the graph is, it is the center plus this. Moreover, if we know that the set is finite, infinite, then 3 or 2 plus 1, and if negation of 2, all other finite cases.
So this is another way, maybe more natural for you.
Yeah, it's just from my point of view as a non-expert, it would be easier for me to read.
Okay, but another reason is that there's 3 points. So this case 1 was proved just in some part of our paper, and we have to use different arguments for point 2. So this is also the case, I think. So maybe formulation could be like you said.
The proof motivates the formulation.
So maybe formulation could be as you said, but proof somehow says that maybe this is also okay. So yeah.
But I agree with you. It's far more systematic. And first to say that the center must be of that form. And under some additional assumptions, so you can have that the center becomes ABC.
Okay.
I agree with you.
This is, yeah, okay.
You should be a referee of papers.
Well, maybe not, because it's not well-paid job.
Well, okay. Well, depends what you referee. If you referee professorship is well paid.
So yeah, so we have analogy between J and our algebra we constructed, and this is what I want to say. And now, what about general case? What about the case when we don't assume that our left path algebra is prime? Because primeness was, I wanted to say that we have a case when we have only one vertex and at least 2 loops. So then we have noncommutative Leavitt path algebra, but it's still simple, and every simple algebra is also prime. So it is the case which is not considered by us, but still in prime class of algebras.
That's just the Kunz algebra too.
Yeah. So now, considering the general case, we'll assume that it's a row finite graph. So this is general assumption for this part of my talk, and this part comes from a paper by Cichocka, Bajo, and Van Wyk and me, and the first part comes from paper by Bajo, Van Wyk and me, not Cichocka.
So there's no problem with something being prime and not row finite.
Yeah, so because the domain-directed fact is very useful. Here, the fact that we assume row finite property is related to available description of the center flat path algebra for such graphs. So this is the reason why we assume.
But it still allows things.
Yeah, still allows things. So the first remark is, or observation, if E is the disjoint union of subgraphs Fi, and each Mi is a maximal commutative subalgebra of LK Fi, then sum of this maximal commutative subalgebras is maximal subalgebra of the sum of these algebras, which is, of course, in this situation, isomorphic to this algebra. So if we have disjoint union, if E is disjoint union, then we have a situation as we have in observation. So this is why we assume that our graph is a connected graph, which means that for what does it mean that we have connected?
May I say? Because I proved the baby theorem about connected graphs. So of course there's combinatorial definition, but it requires a somewhat awkward concept of undirected path. So your graph is connected if every two vertices are connected by an undirected path.
Okay.
And that's combinatorial definition. But you see, when I was lecturing about it during the pandemic, my postdoc asked me a brilliant question. I mean, how about looking at hereditary subsets? And do they define the topology? So first I realized indeed hereditary subsets define the topology. Saturated, no. Saturation is not a closure. Okay? Doesn't satisfy the obvious axioms of a closure. But indeed, the hereditary property defines the topology. So you can declare that if hereditary topology in the sense that open sets are hereditary subsets. And lo and behold, in the usual topological sense, a graph is connected if and only if it is connected in the sense of hereditary topology. If E0, the set of vertices, is connected in the sense of hereditary topology. It's a very simple theorem, and well, I proved it for the fun of it, but it's something that should be in Gene Abrams' book or something, but there isn't.
Okay. Yeah, so we assume that our graph is connected in nature by this observation. So now, still we work with partitions. So now we consider pair of sets A and B, such that A sum B is equal to E0 and the intersection is empty set. But look at this, now we don't assume that A is not empty set or B is not empty set. So in general, A can be empty set or B can be empty set. Now, define D of A. D of A is the set of all elements of A such that from this vertex U, this is set of all vertices belonging to A, such that from this U and from some V from B, I can go to the same point using some possibly two different paths. So I mean from U, I can go somewhere, and from V, I can go to the same point. So there is path from U and some V, not all elements of B, but from some V of B, I can go to the same vertex W, let's call it W, using possibly different paths. It must be the case that the paths are different. The same definition for U of B. Huh? So this is the set of all elements of B, such that there is some U in A, such that from V and U, I can go using some paths to the same vertex. And this part D of A and D of B is called downward directed part of A and B.
I think you remind me what T stands for. What is T?
T is the set of all elements I can go to from U using some part. So this is just a set of all such vertices.
So the set of all vertices you can go to starting from U, or the other way around.
This is the set of all elements I can go to starting from U.
Okay,
Yeah,
that's
exactly.
it.
Exactly.
Okay.
And this is related, of course, to primeness.
Yes.
But look at this. I take U and I need to find some V. Yeah, so not for all, because for primeness, taking U for all elements from B, I can have this situation. But here only, at least for one V, we have T of U intersection T of V is not empty set. The same for D of
So there must exist such a V. You don't care how many you have.
Yeah. But for some V, it must be the situation. The same deal.
Where is V? Can you go on just a second? But it's V is in V and U is, and then it's V the other way around. So wait a second.
So you have, this is our V,
Yes.
our A.
Okay.
This is our V.
Okay, there it is joined.
You take vertex here.
Okay.
You find here such an ending point from path going out from this first vertex and second is the same. Of course, this vertex must be, this ending point must be in A or B. So if this is in A, I have part here, and I have part here. Yeah. So this is D of A. But of course, in A we can have vertices such that we cannot find some V. Okay, so
should we think about D of A as a downward directed closure of A?
yeah, in some sense, yeah. Yeah.
Well, it would be the. Okay, thank you.
Well, by closure, it's a subset.
You have A,
Yes.
and you add to it D of A.
No, D of A is
It's a
subset.
subset of A.
No. So this is not.
Okay.
Yeah. Okay.
My bad.
If we have the case that D of A is A and D of B is B, it can happen. Then we call that the pair AB is called full. We call such pair fully downward directed pair. This is not the same case as for downward directed graphs, because here in this case, for any element from A, I can find some element B in B, according to definition, but not for any element from A and for any element in B. We can find paths with the same ending point. So this is a little bit different. Okay. For any connected, some remarks which are not difficult to prove. For any connected E, if A is non-zero, a non-empty set, and B is non-empty set, then D of A and D of B are also non-empty sets. Okay, so this is the case. And fully downward directed pairs will play a key role in defining commutative subalgebras. So we have example. Consider E and the partition A is UV, so this is UV, and B is W, so D of A is V. Because from V I can go to W, and from W I can go to W, so with paths of length 0. So V is definitely in D of A, but U is not. Because for U I cannot find any element in B, which means that this is W, because from U and W I cannot go to the same point, to the same vertex, using two paths. And D of B is W. So the part AP is not fully downward directed. However, by moving V to B, so if we move V to B, to the set B, so we change partition, in fact we get fully downward directed partition. So it can be seen and checked that if we take B equal W sum V, then indeed.
But I'm confused.
No. I am also confused. Because this is the same symmetric.
Yeah.
So probably this should be U. If we take, yeah,
Yes.
exactly. If we get U, if we move U, yeah, so this is.
Yeah, I agree with you, but not.
Yeah, of course.
Okay.
If we move U to B, so B is U and
Yeah.
W, then we have.
You have two outsiders in the middle, right? Makes sense. But you cannot shift B, it's symmetric.
Yeah, exactly.
I mean, you can, but it doesn't change anything.
So as before, let AB be a partition. As I said, I don't assume that A and B are not empty sets or something like this. The diagonal subalgebra related to AB is the subalgebra generated by all monomials, so as before, such that beginning point is in A and ending point is B. And it's denoted as, you can see. If AB is fully downward directed, we just write LKAB because D of A is exactly A and D of B is B. And it is called fully diagonal subalgebra of Leavitt path algebra related to the partition. Okay. So another example for the graph, as you can see, we can take A equal UV and BW. We get that this subalgebra is generated by F. And if we, so if A is UW, so as we said before, and B is V, which means that this is fully downward directed partition, then our algebra is generated by F star, and G star. Okay, of course, by the nature of partition, always product of two elements of this algebra is zero, still zero. So this is very important.
I'm confused about your notation. What do you mean generated by F? In what sense? It's an idea or what?
Also, you take F and you take product, but F square is zero. So this is, in fact, this is just F.
So you don't consider like V and W, which are the endpoints? No.
No.
You just
this is
F.
F is
The
one
only
element.
and okay, it squares to zero.
Okay. I want to show you only the facts. I want to convince you that description of the center of Leavitt path algebra for row finite graphs is well known. So I just put slides with description of the center just to show that this is well known and described. But I don't want to go into details because this is not the goal of my talk. So this is just we can consider the center of Leavitt path algebra for row finite graph. We know that this is graded by integers. We know what is the part 0. So elements in the center of grade 0 are generated on the basis of this part is B0 described in some way. I don't want to go into details in the sense that to explain what all notation means. And also for any other component, created component, also basis is well known. So this is just to mention that these facts are well known. Okay. So again, called E is row finite graph. AB is fully downward directed partition of the vertex set E0. So our assumption is like this. LK and B denotes the full diagonal subalgebras in this case. And we combine the structure subalgebra with the center to form a new commutative subalgebra inside Leavitt path algebra. So we have the following theorem. Let E be a row finite graph and K a field. If AB is a fully downward directed partition of E0, then for the full diagonal subalgebra, LKAB of LKE, the vector space sum of our fully downward directed subalgebra plus the center of the Leavitt path algebra is always maximal commutative subalgebras.
Now Łukasz is happy because the center appears in the form.
Yeah. So this is always, but this is still not general case, because we have partition which is fully downward directed partition, yeah? But sometimes partition can be not of this nature. But if this is the case, we know that this algebra is maximal commutative subalgebra. Of course, a prime case is one of which is of this nature. I mean, this is generalization of prime case. But still, we want to consider partitions which are not fully downward directed. Still, I have 20 minutes. So now we consider the graph E, like you can see. Then the vertex partition we take is V1, V3, and V2. And this set allows us to explicitly describe the center and the full diagonal subalgebra. Okay? As before, as we noticed, if we take V1 and V3 for A, indeed this is fully downward directed graph. And the center of the algebra has basis identity, because this is sum of all vertices, so this is identity. And if we take all elements f, c to the n, f star plus c to the n.
But isn't V1?
Where c is cycle and f is this.
But isn't this sum V1 plus V2 plus V3 equal to 1?
This is equal to 1, yeah, exactly. But to indicate that this is the element related to this sum. Yeah, so this part, as I said, the term V1 plus V2 represents the vertex to central elements, and the element fc to the n, f star plus c to the n correspond to the cyclic symmetries contributed by the loop C. And this is a basis of the algebra. This is the center, this is basis of the center of our algebra. Okay? The full diagonal subalgebra related to our partition is the set consisting f star, e star, and all elements c to the n f star. So this is our fully diagonal subalgebra. Okay. So this is the case for this. And combining these two structures using theorem, we have for this specific case, we can describe exactly what is our maximal commutative subalgebra we construct in this case. Okay, but okay, so I will omit it. Okay, so now we want to move to general case in the sense that we don't assume that we have fully downward directed or something like this. So suppose that we have general case, we have just partition. Then we defined elements u of A and u of B. What is u of A? U of A is just a set which can be defined in the way you can see, but this is exactly A minus D of A. Okay? U of B is B minus D of B. And in fact, if we have D of A, this is D of B, then we have U of A, which is disjoint, and U of B. Okay? And then, if we take vertex here, we always can find some vertex here, such that from here we can go, for example, here. But if we take an element here, and we have path, this path must be inside U of A, in the sense that ending point of this path must be in U of A. Also, the same is in for U of B. And if we take an element here, we can go only out of this here. Also, from here, we can go from here to here. and we cannot go from UA to DA or DB, the same for U of B. So this is just part which only this U of A is the set of vertices such that parts, all parts which has ending point in U of A has beginning point in D of A or in U of A. So this part is not related to B somehow. Okay, so we have 4 sets. In fact, we have new partition of our set E0. We have disjoint, 4 disjoint sets. Some facts about them, but they are not important. They are important for proofs, but I don't present proofs, so only I put some information that we have some conditions on the sets. And now, for our U, we consider the ideal that algebra generated by all vertices in U, and we define new graph such that the set of vertices of this new graph is just E0 minus U. We remove all edges from our graph such that ending point of HE is in U. So we take only such edges that ending point is not in U. And of course, we consider R and S for such edges.
Okay, and now that's the point. I know it's not your fault because this is what is in the literature, but this is the most stupid and preposterous terminology you can possibly fathom. Because you're not taking any quotient, you're taking a subgraph. So why on earth call it quotient? Quotient means identifying things, not removing things. It's one of these absolutely, totally idiotic terminologies used in Leavitt.
But it is somehow...
But it's a quotient of algebras, but you should not confuse it.
Okay.
Yeah, I mean, it's because it introduces so... I'm sorry I'm so furious about it, but it introduces so much mess into the terminology. So we consistently fight with terminology, and we call them, subgraphs, admissible subgraphs. Okay. And especially that there's so much of beautiful factoriality in here. Really, honestly, I mean, there's so much you can read out of relations between graphs, isomorphisms between algebras. So why confuse it? One thing is about graphs, one thing is about algebras. In this case, this is a contravariant functor. So you should not call it like this, but it's in the literature. It's in Abraham's book. And also, I think that people doing graph sister algebras are equally sinful of sick terminology. Okay, sorry about this outburst of my anger with it, but this is a very a very prominent example of spoiling mathematical terminology, and sometimes it's hard to repair it because it's been so deeply engraved into the terminology that 90% of the people will say mindlessly quotient graph without thinking that it is something. Yeah. Sorry about that.
So now we consider for this graph E divided by U, I will call it this way, the map C from left path algebra to this new left path algebra for new graph. A definition is that C of V is just V if V is not in U, and this is 0 if V is in U. C of E is E if E is ending point of E is not in U, and this is 0 if ending point of E is in U, and the same for E star. And it occurs that it extends to a K algebra epimorphism of Z-graded algebras, because this algebras are, of course, Z-graded. The kernel of C is just ideal generated by all vertices of U, and we know that the left path algebra for E divided by U is isomorphic to the algebra Leavitt path algebra divided by the ideal E of U. So these facts are well known in literature. Now I want to present you some lemma, because this was almost proving our results. It was almost everything was almost done, and then we appeared, or we we found some problem which was fixed by the following lemma. The problem is very, very specific, but very also important. So I wanted to present this lemma because I had to spend a few days to think about the situation, but finally this lemma helps. If psi is a cycle in E divided by U that has no exit in U divided by U, then C has also no exits in E. So if we forget about all vertices in U, and we have some vertex, some cycle, and this cycle doesn't have exits, then taking into account all vertices in U also, we still don't have exits.
Could you for a second go to the previous slide? Yeah. What can you remind me what you assume about the set U?
Set U is the set which is sum of all elements belonging to A, but not to the dA.
So it
Means that taking element in U of A, I cannot find something in B such that I can find common vertex and two paths going from first vertex and second.
Yeah, but this is a very specific construction.
Yeah.
My question is whether U is automatically hereditary. Because if U is not hereditary, then
Yeah, this is hereditary.
you see, because in fact you can prove that with subgraph E mod U is a subgraph if and only if U is hereditary. Because otherwise you simply arrange and source out.
Yeah. So this is hereditary.
So it must be hereditary. This is what I wanted to
exactly.
double check. Okay, so makes perfect sense.
So previously there was U of A and U of B, and
But U is sum of the sets.
Okay.
I think.
So we have lemma, which I am proud of. Now we have something which is called commutative core. I want to recall you, it was defined by G. Canto and Nas Sfahani. This is subalgebra generated by all elements of the form alpha alpha star, alpha C alpha star, and alpha C star alpha star, where C is a cycle without exits. And we know that every this subalgebra MK of E is always maximal commutative subalgebra. But this is totally different than our construction. Okay, but using these conditions and notations, we consider for our U. We consider for our U, subalgebra of Leavitt-Path algebra generated by all such elements. So all such elements as generate commutative core. And we take only these elements that ending point of alpha is in U. Okay? So not all of them, but ending point must be in U. Okay, and the main general case.
And why do you call it core? Because typically core for Leavitt-Path algebras means gauge action invariant subalgebras, but they are not gauge action invariant.
So why? I don't know why this is commutative core. It's called.
Yeah, why it's commutative is clear, but why is it core? Because you know when you say about the core of say AF core of graph sister algebra, it means gauge invariant subalgebra, which must be AF. Okay,
so I cannot explain.
That somehow contradicts
There is some
terminology. Right, Francesco? Am I right? Francesco? Well, he is, but
okay. So the main result is let E be a row finite graph, and K is a field for any partition. So taking any partition, if we take space, vector space, our LK of dA dB constructed before, we have a pre-image of the center of Leavitt-Path algebra for our quotient graph, plus this part of commutative correlated to U. This subspace is always maximal commutative subalgebra of Leavitt-Path algebra.
can you remind me this psi, what it is?
So this is pre-image of. This is psi. So we take center here and we take pre-image.
Okay.
so elements. So the sum of the three components gives us maximal commutative subalgebra. Always. And the following facts are very interesting for me, at least for me. If AB is fully downward directed, then we can show that U is an empty set and it's not difficult. And we get what we proved using this theorem, this general theorem. If U is E0, because it can be, for example, in the case that A is E0 and B is empty set, then U is E0, then we get commutative core. So our construction means that up to partition, we take bigger and bigger this part, which is just related to our construction, and smaller part related to commutative core, or if, if sum of the sets is smaller and smaller, D of A sum D of B, then MK of U is bigger and bigger. So this is just kind of intuition, not exact mathematics, but this is kind of intuition. So we move from first part of this algebra to the last part of algebra, changing partition.
And how do you use row finiteness? How does it play?
So row finite, we assume here because, as I said, we have good and explicit description of the center for row finite. So everywhere we use the fact about center. We know how.
Yes.
Yeah. And that's all I prepared. I think that I have. Sorry. Yeah, I have translate.
Okay, thank you very much for that. Okay, so now we can begin our discussion.
Thank you very much for being here during the talk.
Adam.
No, I just clapped my hands.
So you have no questions?
No, I'm happy.
Okay, Francesco. Hello, Francesco. I don't know why he's here, but okay. Anybody else? Ludwig, Zach, come on, guys.
Yeah. So maybe I will.
Okay, Ludwig, wait. Oh no, Zach.
Well, no, I'm fairly familiar with this, but very nice talk and good to see you all.
Yeah.
Okay, great.
So I want to, since Zach said something, I want to add that together with Zach and Anna Cichocka, we published recently a paper about Steinberg algebras, which is, but for prime case, which is generalization of our left path algebra case. And in fact, we using our results, we can produce even more maximal commutative subalgebras. So bigger class than for left path algebras case. So I still open questions to consider maximal commutative subalgebras of Steinberg algebra for general case, not prime case. So the result is very nice, I think.
And I understand that Steinberg algebras generalize Leavitt, right?
Yeah. But it also generalizes Commutative algebra. So
yeah.
Using our paper, you can produce in different contexts some maximal commutative subalgebras.
I'm wondering, isn't it the case that what does massa stand for? There are many people who consider the massa, that isn't maximal abelian subalgebra. I don't know.
Yes, it's correct. Maximal abelian subalgebra. Precisely.
Okay. So you see,
Is it the same?
Yeah. Yes, exactly.
Commutative subalgebra.
Yeah, abelian is commutative.
Yeah. So.
So you see, because I know many talks in which people in functional analysis in sister algebra study massas. Right, Adam?
Yes, that's right. And I think that the reason is very pragmatic, that if you want substitute A with C, you would get what? MC Maximal abelian subalgebra MCSA, and this is hard to pronounce, and massa is easier to pronounce. And I think that this is the only reason.
Yeah, of course. But I even remember the guy, Simon Wasserman from Britain, I believe. He with many papers and many talks about massas of sister algebras. So that's I'm happy because it's apparently important, not just pure algebra, but in bigger.
Curious fact, I just recently learned that the Calkin algebra admits 2 to the power continuum of different massas, which is amazing.
Wow, that's quite a lot. And okay, just a very naive question. So Steinberg is one generalization, and how about other generalizations? Like how about going to Kuhn-Spilsner algebras or going to topological graphs?
Yeah, so
That's would be interesting.
yeah, it would be.
How this plays a role, because Comte and Pascal is higher rank graphs. So this is already one direction in sense, right? The Steinberg and Comte and Pascal. This goes well. Okay, I have one last naive question. How much of your work survives when you move to the completion of the graph sister algebras?
I don't know. I cannot answer. Yeah. So as I said, yeah. So I have never worked in sister algebra. So this is not kind of my world. So I don't have any feeling about that. But it can be that it survives somebody.
I have a strong feeling that it does because look, I mean, Leavitt is dense inside. So just in general, let's ask ourselves a stupid student-like question. Imagine that I have a dense subalgebra in a sister algebra, and I have a maximal abelian subalgebra in this dense subalgebra. So can it be that it's no longer, of course, it remains abelian, right? Because it's subalgebra, but can it lose maximality? That will have something which is in the limit. And it's non-algebraic, and it still goes into this and commutes. I don't know. I find it hard to
That's a good question.
Yeah.
My feeling is that the answer would be negative, Piotr, since commutants are automatically von Neumann algebras.
Okay. Thank you, Adam. I was hoping for such a yes. Yeah. So that should survive. Yeah. And this would be by some simple argument like Adam just mentioned.
Yeah. Mm-hmm.
Yeah. But let me take this opportunity to mention that there is a completely, in my opinion, surprising feature of Leavitt path algebras, is that though they are not closed on the holomorphic calculus or any such fancy stuff, the K-theory is, under some assumptions, is basically the same as that of graph sister algebras. And that's totally remarkable because K-theory is really computable only for Banach algebras. Algebraic K-theory is notoriously not computable. And if you just take a polynomial algebra inside a sister algebra, you typically know nothing. You need some assumptions, like, that inverses belong to algebra, basically. Okay, because in a sister algebra, every positive element is invertible, and that makes a whole lot of difference when you do K-theory. And still, for some absolutely remarkable fact, this is the work of MICHAۯ and other people, is that K-theory of Leavitt path algebras happens to coincide under some assumptions with that of graph sister algebras, which is totally non-obvious. So that kind of a survival is non-obvious. The survival of massas is, I suppose, easy. Okay, so let us thank Michał again for his beautiful talk.
I have a question. One last question.
Yeah.
Mine would be more quantitative, because in the beginning, when you gave the motivating example, you've said that we don't know how many maximal commutative subalgebras we have in matrices. And here you got the formula for many
But this is only
commutative
kind of
algebras.
class.
Yeah, but I wanted to ask first of all whether or not each partition gives you a different algebra or not, because it's, at least for me, not obvious whether or not when you change A and B that you necessarily get a different maximal commutative subalgebra for a given graph, and that each time you get the different algebra, and moreover whether or not this could lead in any way to any bound from the below for the amount of algebras for matrices.
So I don't know answer because yeah. So this is
It's just something you
why I
haven't.
think about yeah. Yeah.
It's just that the motivating example stayed with me, so I decided that I should ask because just looking at this formula, depending on d of A, d of B, and U, it's not obvious how this algebra changes when we change A and B.
Yeah, so I don't know if they are, in some cases they are isomorphic, I don't know, or something like this. Yeah, so yeah. But even for matrices, if we take different K1 and K2, we get probably different dimension for our algebra, which is this gray block plus the center. So they are not isomorphic since they are not of the same dimension. But when they are isomorphic, even for matrices, I have not thought about that. And also the same for left-part algebra. So about changing partitions, I don't know when it can be and when they are isomorphic or something like this. I don't know.
Okay.
That's a very good question.
Yeah, very good question. Yeah.
Okay, so okay, so let us thank Michał again for a very.
Thank you very much.
Thank you.
Thank you.
Bye-bye.
Let me stop recording.